Okay, so you can look at this. So right now we are doing analysis of transistor amplifier using parameter model. The previous class you can see that I covered hybrid parameter model and how to determine edge parameters graphically. Also we have given definitions for each one of the hybrid parameters. In today's class we will use hybrid parameters to analyze the circuit for transistor amplifier. So transistor amplifier is one of the important circuit. It is based on bipolar transistor. Even though here we are not an actual circuit, but it is a block-based circuit which is written. Here our intention is to just concentrate on other parameters apart from the amplifier. You can see here there is a Vs which is source voltage, which we labeled as Vs, and corresponding to this the current which is taking, which is A is the current corresponding to Vs, and of course this is the Rs is the resistance of this power supply. Okay, this does not come into the picture of transistor. Even every power supply will have some resistance internal to that, and this is Rs nothing but which is a source resistance. Resistance of this power supply, which we shown here externally, and certainly it is an input impedance of this transistor amplifier. Looking at these 2 points, what is the impedance offered by this amplifier? Ideally, this value must be very high. Okay, ideally this value must be an infinite. Okay, then this amplifier will be very good. And also look at that Z must be 0 ideally, so that amplifier is very good. For practical amplifiers, Zi will be very large and Z will be a very small value. And look at this, this is the current which is from the amplifier, which we indicate as I0, which is output current, and the amplifier, the output voltage which is produced by the amplifier, which we label as V0. And do not worry about directions of this current I0 and as well as IA. They only assume the directions here. Later on, they can change directions depending upon the current. And also look at that the amplified signal which will get broadcast is low resistor, which is R. So this is the tapered transistor amplifier which is shown in terms of the block diagram. And now we will apply hybrid parameter model for this transistor amplifier to analyze this amplifier in more details. Normally in the examination point of view, we ask the derivations such as current gain, input impedance, output impedance, and so many other parameters are there. So here you are seeing the one derivation which is current gain, also called as current amplification factor. Okay. So before we go to the derivations, let's look at this. The same circuit has been written in detail with graph diagram replaced with hybrid parameters. You can see that in this, what is the change which you can observe from block-based transistor amplifier to that of hybrid equivalent representation of amplifier. You can see a transistor amplifier replaced with HI. This indicates the resistance, input resistance. Also, look at there is a voltage source, HR times V0 is the voltage source. There is a current source, HR times IA. That means this current source depends upon the current flowing here. This is not an ordinary current source, it is a dependent current source. Also, this voltage here depends upon the voltage across the output. You can see the magnitude of this voltage, HR times V0. HR is nothing but it's a reverse voltage gain, and V0 is nothing but the so this is a current source, and even this H0 indicates an admittance. That means the transistor amplifier has been replaced with HI, HRV0, HF into IA current source, and H0 which is an admittance. Apart from that, this complete other rest of the elements have been added as it is. So you can see that there is RL here, and even there is RL here, which are not energy changes. And even there is a IA current which will indicate the same, and we can see there is a voltage source here. This is signal to be amplified, and RS is nothing but as we said, this is the resistance of this power supply. Every power supply will have some resistance. So this diagram shows the generalized H parameter model of a transistor based amplifier. We are doing here the complete H parameter model. You have seen that earlier. We can even write this H parameter as simplified version by just neglecting this HR times V0. If you neglect this, the complete model becomes a simplified model. So that's why here we are doing for the time being the analysis of transistor based amplifier using complete H parameter. So this is the complete H parameter model. Okay. So this model, in examination point of view, they will ask you to derive the expressions for the current gain of this this transistor amplifier, voltage gain of this transistor amplifier, and even the input as well as output impedances such as certain as well as for these things we can derive mathematical expressions. So we start with deriving an mathematical expression for current gain or current amplification factor. See, all these derivations are based on this circuit, and this circuit is in turn based on this circuit. We started with the block diagram, later on we replaced this block diagram with hybrid parameter, and using this the H parameter we are going to derive various parameters of the transistor amplifier. The one such parameter is current gain. Look at this from the circuit, everything has been written from the circuit. It is all these derivations. If you can see here, A is nothing but notation which is used for current gain. A stands for gain, and substitute here I stands for it is a current gain. So A indicates it's a current gain. There are two current gains which you must note here. One is A without considering source resistance, and AIS is there. You can see that substitute here. And AIS is a current gain with considering RS, and A is nothing but current gain without considering RS. Okay. There are two criteria are there. And you may consider this existence of this, or you may ignore the existence of this. So first we derive the expression for current gain by ignoring existence of the source resistance. You can see that as per the definition, what is the current gain? It is nothing but output current by the input current. Look at the circuit here. IM is nothing but load current, and input current is nothing but the IM. Okay, that's what we written here. IM by IM. It's nothing but as per the definition. So this is from the definition we have written this. Okay, there is no proof for those kind of things. No, from the definition you can write. Also look at from the circuit, IM is equal to minus of I0. Look at the direction of I0 as well as I0. I0 is nothing but assume the direction of through-port H parameter model, and I is nothing but actual load current is going into the load. So obviously this assumed current is opposite in direction as that compared with the load current here. You see that any amplifier current will flow to the load, but in H parameter model you have taken the current as going into the block. So obviously these two currents will be in opposite in direction. So that's why I can write here based on this directions. I can write I is equal to, how do we indicate opposite direction? That will indicate a negative sign. So I is equal to minus times I0. If you substitute this here, so expression for definition for current gain becomes minus I0 divided by I. Okay, that's going to be the equation number 2. And before we go to the further, we proceed the expression for A. What you can do is apply KCL to the output section of the filter. You can see here. This is going to be my point here node. At this point, if you apply the KCL, which of the current law, if you apply the what is at this particular point, calculate the directions of the, find out the directions of the current. How many currents which are going out, how many currents which are entering this node. Which you can see here, there is one current which is leaving this node, and you can see this current also is leaving the node. Even though this is admittance here, you multiply this with voltage that gives you the current here. Don't take it only H0. H0 will not give you the current. H0 multiplied with voltage across these 2 points B and B dash that gives you the current here. Just multiply H0 with V0. And other current which is nothing but IL. You can see here I0 is given by the current which is entering is equal to what are the other 2 currents which are leaving. Because at this point this current is entering, other 2 currents are, one is towards H0, other one is towards the HF into IA. So these 2 currents are leaving and this current is entering. So obviously direction of I0 will be opposite of these 2 directions. This is one current, this is another current. There is a current flowing as per the arrow direction which has been shown here, and H0 times V0 is a different current flowing here. Okay. If you want, you can indicate the direction of current here. This current is nothing but H0 times the V0. This is the current flowing in this admittance. It is H0 times the V0. So obviously these 2 currents are leaving and this current is entering. So as per the KCL, the entering current, which is I0, is equal to leaving current, sum of the leaving currents. So this we have labeled as equation number 6. Equation number 3. Any questions about that? So look at now, next what we can write is the voltage drop across this, which we can indicate as V0. This particular voltage, I cannot able to show here. Actually the voltage V0 is nothing but across V and V dash. I am going here outside. So V0 is nothing but what is the voltage across this? IL times the RL. So IL times RL, which also can be written as, because you can see here IL is equal to minus I0. As per this we can write this one as V0 is equal to minus I0 times RL. Let us call this as equation number 4. So we can substitute equation number 4 and equation number 3. That's what we done here. So I naught as it is, HF times I as it is kept, but in place of V naught here you can see that we substituted as minus I naught times R. Okay. So now we can rest of the thing is only simplification here. We have I naught term on the left hand side. Even we have I naught terms on the right hand side. Just bring it to the left hand side and take out I naught as a common factor. As you can see here, I naught is equal to I naught into 1 plus H naught into RL, which is equal to HF times IA. This term we kept as it is. I just want the ratio of I naught by IA, because that's our definition of current gain, I naught by IA. So as you can see here, as per our definition, A is equal to minus I naught by IA. They take on this same definition, equation number 2. But look at here, I naught by IA from this equation can be written as HF times divided by this factor. So that can be written as minus, you can keep it as it is, but instead of I naught by IA, you can write as HF divided by 1 plus H naught times R. Okay. This is going to be the expression for current gain, ignoring source of resistance. Okay. Because here nowhere we considered the RS into in our derivation. So that's why this is going to be the expression. Here it indicates a current gain expression without considering RS. Okay, you need to remember these equations. That's why I highlighted this in block diagram, because this usually in the case of solving problems in examination, if they give you the HF, H0 and RL, it has to calculate current gain, you can use this equation. So you need to memorize all these equations for problems solving. And coming back to the next is, if I consider the source resistance, this now the expression will change. You can see that we are going to derive the expression, current gain expression by considering the source resistance. Okay, most of the time we will ignore the source resistance, but if you consider even this, the contribution will be added. The current expression what you are seeing is this is the current gain expression by considering RS. Look at now what we have done here. Before we proceed the derivation, what we have done is for the input side, what you are seeing here, Ds as well as RS, you can see here, Ds as well as RS. The rest of the circuit are replaced with the Zi. Okay, you can see here from here onwards, whatever the impedance of the circuit are replaced with Zi. Zi indicates an input impedance, which is the impedance at these two points of an amplifier. So rest of the circuits are going to replace with Zi. That's what you are seeing. Questions about this input section of an amplifier? Have you understood how to get this one? So what I am doing is rest of the amplifier I am replacing with Zi. Normally when the current starts flowing here, what you will experience is a resistance, that's all. So I will replace this rest of the circuit with resistance offered by this current, or this current, which is nothing but Zi. This one will be the circuit. The rest of the simplification, what I have done is this voltage source in series with resistance. I converted this into the current source in parallel with resistance. Okay. This change what I made here. Voltage source series with resistance is equivalent to current source in parallel with resistance. Right? As per the Ohm's law, not Ohm's equivalent. This is called as not Ohm's equivalent. Okay. So not Ohm's equivalent, what it says is if you have a voltage source and if you have a resistance in series with that, you can replace this voltage source and current source, voltage source and resistance by a current source in parallel with the resistance. Okay. And this Zi is kept as it is. All of you understood this change here? How we have done this circuit from the original input section. This has been extracted. From this video, what we have done is we have calculated not equivalent circuit by converting voltage source and resistance in current source parallel with the resistance. Rest of is simplification. Let's go as per the definition. Now here definition for if you consider RS, definition will change. If you don't consider RS, this is the definition of current gain. But if you consider the RS, I am going to indicate new notation AIS, current gain by adding here S indicates that I am considering the source resistance. You can see here minus I0 times IS. In place of here II, okay, if you consider just this current, okay, that means you are not going to consider the RS. In place of II, if you replace with IS, which you can see here, minus I0 divided by IS. That means instead of II, I added here as IS. That means because of RS, which I am going to consider. And look at that, all of it should y is negative sign. If I want to ignore this negative sign, the definition will be AIS will be IL by IS. Okay, one step I have just the skip here. If I want to indicate negative sign, then definitely minus I0 divided by IS. this also can be written as IS divided by IS. If you want to indicate the positive sign. So this is 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 replaced with minus I naught divided by IS. This is equal to the definition. That's for the definition by considering source resistance. Okay. Now next you can see here what I did is just multiply and divide this numerator and denominator by IA. That's what we done here. You can see here minus I naught as this in place of denominator value here IA. And again I am going to multiply with IA because these two cancels and we will get back the same expression. Okay. I just multiplied and divided this equation number 5 by IA. You will see later why this has been done. And this you can see that minus I naught by IA can be written as A. Look at the definition as per the equation number 2. Minus I naught by A can be written as AI. So minus I naught by A can be written as A, but IA by IS I can as this. Now you can see that definition AIS is equal to AI times IA by IS. Now can we obtain the expression for IA by IS looking at this R2 equivalent? That's what we done here. Okay, I written here, but IA is equal to IS times RS divided by RS plus ZI. This is written based on the current division rule of the Norton's equivalent. If you can see here, this current I am going to calculate. IA is equal to, is just apply current division rule here. How to apply current division rule? If you want to calculate this current, just take source current, multiply with this resistance, divided by sum of the resistance. That's what I have done here. IA is equal to IS source current multiplied with RS, this particular resistor, divided by sum of these two resistors, divided by RS plus ZI. Okay, this is nothing but how we obtain this is based on current division rule. So based on the current division rule, one can write this expression. Explaining this is not convenient because this is actually the basics of electrical networks. Okay, and now I can explain you how I got this expression. For the time being, don't worry about this current division rule. Simple technique is you want to obtain this particular current, then just multiply the source current with the resistance and divide by sum of the resistances. A simple mechanism you learn it. That's all. Okay. Otherwise, you can derive this expression, not a problem at all. But this will take more time to derive. You have to go through the basics of this current division and then you have to write it here. Yes, you have to assume that some current flowing here, another current is flowing here, just this current will be equal to sum of these two currents. If you simplify that, definitely you will come out with this. For the time being, you don't waste your time by deriving this. Our intention is not to derive this. Our intention is to derive the expression for current division. Now you can see here this expression is related with IA as well as IS. As you look at as per the definition, there is IA by IS here also. Now can you substitute this in place of IA by IS as RS divided by RS plus ZI? If you do that, then you will come out with the equation for the IS. So IS is equal to this IA capacity, but in place of IA by IS, which you can write as RS divided by RS plus ZI. So this is the final expression for current gain by considering source resistance. Now my question is now, if I make this equation RS is equal to infinity, what will be the simplified expression? I am going to substitute RS as infinity. So obviously this AS becomes equal to here. Because you see that if you bring this RS to the denominator, this RS will cancel with this RS will left out with 1. But look at here, ZI by RS becomes. Substitute RS as infinity. That means you are left out with only 1 here in the denominator. So that means AS becomes equal to A. So what is the conclusion from that? Then actually the current gain by considering RS. If you make RS as infinity, Okay, if you take rs as infinity, then this expression becomes same as this expression. Understand? Let's say conclusion from this derivation. Go through this. This is the first equation from this representation. We have other two derivations. Take up next derivation is input impedance.
what are the lab in morning? ECI lab. Someone ma'am is a lab man. My mistake. Check your guys.
Derivation. Input impedance as per the definition is Zi is equal to Vi by Ia. This will be called as equation 1. Okay, this is from the definition. Okay, it's a ratio of input voltage by input current that gives the impedance. So next is you apply KVL to the input section of this figure shown in figure B for this. If you apply KVL to this, you can see here. Between these 2 points, between A and A dash, the voltage which is present between the plus Pi, which is equal to drop across. This is Ia times Hi. There is a first term, and plus drop across this particular voltage source, which we consider as HR times V0. So between these 2 points, it is Vi minus Vi Hi times Ia plus HR times V0 that gives you the Kirchhoff voltage equation. Let's take out as equation number 2. Substitute 2 in equation 1 for the Vi, so that we get the expression as Zi is equal to Hi plus HR times V0, the numerator portion divided by Ia plus this. And you can also substitute for V0 in obtain the expression for V0. V0 is equal to minus I0 times R, which you can see previous derivation. And this minus I0 can also be written as A times Ia. Any questions about this? Look at previous derivation. So in place of you can look at definition for A. So A is nothing but minus I0 times divided by Ia, right? Just we cross multiply this. So minus I0 can be written as A times A times A and R times this. And we got as equation number 4. And substitute V0 in this equation number 3. So Zi will be as this Ia plus HR times in place of V0. You can see Ia times R and Ia is left as this. The simple thing is we simplify this equation. Ia is here and here, it cancels out, and this Ia also is here, it also cancels out with this. Therefore, in the first term is Hi plus HR Ia R as this. Okay, that we call as equation number 5. Further, we have simplification for equation number 5. So here you only obtain from the previous derivation current gain without considering Rs. Then you can substitute in place of Ia here. Okay, if you do that, Zi is equal to Hi plus HR as this. You can see here for A expression is minus HR times divided by 1 plus H0 into R. Just simplify this. So Hi as this minus got taken out and minus HR R divided by 1 plus H0 into R. So this is the expression for the impedance of classical base parameter amplifier. Next is going to be the voltage V. So all these derivations you must practice, otherwise it's very difficult to write in examination. voltage gain expression. So this is from the definition which you can write AV is equal to V naught by VI. So equation number 1 is from the definition. Okay. And you can see equation number 2 what we have manipulated. In place of V naught we substituted as AI times R. You can see previous derivation. Okay. And VI is capacity, so this is equation number 2. And you can see here in place of VI divided by Zi, this I can be brought here, so that VI by I can be written as Zi divided by this equation number 2. So look at equation number 3. If you do that, AV is equal to VI times Rn divided by Zi. And you can see further this becomes an voltage gain by without considering Rs. If we consider Rs, this equation will change. That's what we follow next. Voltage gain by considering Rs is derived as follows. AVS from the definition is V naught by Vs, which you can see without considering Rs, AV is nothing but not V naught by VA. So just have added here Vs into the denominator. So AVS becomes V naught by Vs. And this equation number 4 can be manipulated here V naught by writing multiplying dividing this equation by VA. If you multiply and divide by VA, you get equation number 5. AVS is equal to V naught by VA into VA by Vs. Also we can get from V naught by VA is equal to AV. Okay, V naught by VA can be substituted as AV. So that is the case AVS becomes equal to AV times VA by Vs. Up to this is from the derivation. But beyond this, if you want to proceed, you need to consider back the circuit. You can see here the circuit input section is written here with Vs, Rs, but rest of the circuit has been replaced with the impedance of this array. Okay, using this circuit, also look at that thus the Zi, the voltage is taken as Vi. Now, can we obtain a mathematical expression which will relate Va as well as Vs, apply voltage division rule? So Va can be written as Vs times Zi divided by Rs plus Zi. This is by voltage division rule. If you apply voltage division rule, you will come out with the equation this 7. Okay. So Va is equal to Vs times Zi divided by Rs plus Zi. Just take the send this to denominator. So Va by Vs becomes equal to Zi divided by Rs plus Zi. So from the equation number 7 you can substitute back in equation number 6. You will obtain the final expression for AVS. AVS is equal to this AV is kept as it is, and instead of VA by Vs, you can write as Zi divided by Rs plus Zi. So in this equation, if you make it Rs as 0, Rs tends to be 0. So that means if you make Rs as 0, Zi will cancel out, and therefore this AVS becomes equal to AV. That's what AVS becomes equal to AV. That means in this circuit, if you make Rs as 0, that means the voltage gain without considering the source resistance becomes equal to the split considering source resistance. That means the voltage gain without considering source resistance is AV. This becomes equal to this AVS if I make Rs as 0. So go through this simple derivation, and we will refer to the last derivation, which is output admittance. Go through this. If you have any questions, you can ask.